Hi and welcome to my OCR A-level biology revision session with me, Christine. So today's lesson I want to look at the action potential, which is part of your neuronal communication topic area. So let's just understand what it means when a cell is in what's known as its resting state. So the resting state of a cell is where there is a resting potential. Now what that means is that there is a potential difference across the plasma membrane. Now that's normally about minus 70 millivolts. So it means that there is more ions on one side compared to the other side. Now we have positive ions and we have negative ions. And what we're saying is that there are more negative difference inside compared to outside. Now this is actually also about these positive ions, and we're specifically going to look at sodium and potassium and how they play a role in maintaining that resting potential at minus 70 millivolts. So we know that there is a resting potential, and that is maintained by our sodium-potassium pump. Now, our sodium-potassium pump is always pumping 3 sodium out. That's because it's going against a concentration gradient. ATP is required to be hydrolyzed for the pumping process. 3 sodium are going to be pumped out, and 2 potassium are going to be pumped in. Now what that's going to create is a high potassium concentration inside the axon and a low sodium concentration inside compared to outside. Now, remember we're talking about a membrane that is a barrier that will only allow ions in or out because they are charged. It will only allow them in or out if there is a channel or a carrier protein present. So you can see in my axon plasma membrane that I have a channel which is a sodium channel, but it is closed. It's not going to let any sodium into the membrane. However, there is a potassium channel which is open, which means potassium can leave down its concentration gradient. Now, we don't tend to use the term concentration gradient when we're talking about ions. What we actually use is we talk about their electrical chemical gradient, which basically means the concentration gradient of the ions. So we know that there is a high potassium concentration inside and a low sodium concentration inside. We know we've created this electrical chemical gradient, and we know that our membrane potential is minus 70 millivolts, so our cell is in its resting state. So what happens then to the membrane if that resting state, that minus 70 millivolts, is deviated away from? Well, this is where we need to look at the other proteins which are found in that membrane. So we know we've got a sodium-potassium pump. Well, we also know that there are voltage-gated sodium channels and voltage-gated potassium channels. So if we were to move away from our membrane potential and we were to move towards what's known as a threshold value, if we don't reach the threshold value, what will happen is the membrane potential will be brought back to its resting state. So if we do not have a stimulus that reaches that threshold value, those voltage-gated channels will remain closed. So they're voltage gated, which means only when a specific voltage is reached will they be activated to open, or will they be activated to close. So it's important that we note that that membrane is always going to be brought back to its resting state if our stimulus does not reach that threshold value. So what happens if it does? Well, if the stimulus actually reaches the threshold value, then this will trigger what's known as an action potential. Now, an action potential is what we refer to as our nerve impulse. Now, this action potential is going to be propagated down the neuron. So propagated down the neuron basically means it's going to move from one end all the way down to the other end. And it does that through a set of stages. And the first one is the minute we have reached our threshold value, our voltage gated sodium channels are going to open. We open the doors, the sodium is going to flood into that axon, and it's going to flood in down its electrochemical gradient. So depolarization is where the sodium is moving in, and it's moving in down its electrical chemical gradient. Those voltage gated sodium channels are open, more sodium is going to be flooding in. So what we have is the sodium is able to move in because the channel is now open. It's in electrical chemical gradient. They will flow down their electrical chemical gradient, so into that axon. So once we have depolarized the membrane, once it gets to its peak, which is about plus 40 millivolts, it's always the same size. So an action potential never goes above the plus 40 millivolts. So once the membrane potential has reached that plus 40 millivolts, the voltage gated sodium channels are now going to close. Now what's going to happen is what's known as repolarization. We're going to take that membrane potential and bring it back down towards the minus 70 millivolts. We are going to repolarize the membrane. The voltage gated potassium channels now are going to open. Potassium ions are going to flood out. Why? They're going to go down their electrical chemical gradient. They're going to flow from where there was a high concentration to where there was a low concentration, so down that electrical chemical gradient. So what we're saying is there's a higher concentration inside because we've opened these voltage gated potassium channels. The potassium now floods out. So what happens then when we go past that resting state? So we've overshot the minus 70 millivolts. We've gone past that resting state. This is where we call it hyperpolarization. So hyperpolarization is what's known as the overshooting past that minus 70 millivolts. Our voltage gated sodium channels remain closed. Our voltage gated potassium channels now close, and our sodium potassium pump is going to return our membrane to that resting state. So it's important that we understand during hyperpolarization we have what's known as a refractory period. Now this is important to note because if I have depolarization and my voltage gated sodium channels have opened, my sodium is going to move in. It's going to diffuse from an area of high concentration to an area of low concentration. That's going to mean that the resting membrane is going to depolarize towards its threshold value further down the axon, and that's called by local current. And it's a way of positive feedback in the fact that if we are moving those sodium ions down through the axon, that is going to make that membrane become more positive, moving towards that threshold value. Well, what's going to happen is we're going to have our sodium channels, our voltage gated sodium channels opening. Our repolarization is going to happen because we depolarized before, we're now repolarizing. We're now depolarizing further down because we want this action potential to propagate down the axon. So the action potential needs to move along in one direction. Well, because we have now depolarized, our voltage gated sodium channels have opened. Our sodium is going to move in because we've reached the threshold value. But they've moved in both directions because, remember, the sodium will diffuse, and it will diffuse in both directions because it will go from an area of high concentration where it's just moved into the axon to a lower concentration away from the entry point. Well, if we didn't make sure that our voltage gated sodium channels remain closed, i.e. we didn't get to hyperpolarization, we didn't get to that refractory period, what would happen is those sodium channels to the left would then open and the sodium would flood in and the impulse would go in the wrong direction. So by getting to that point where we overshoot that resting state, we go past the minus 70 millivolts, we maintain that those voltage gated sodium channels are going to remain closed, and therefore the action potential is going to be propagated down the axon in one direction. So let's just look at this all together, because what we have is a nerve impulse are always all or nothing responses. If the stimulus is going to reach that threshold value, the action potential will be triggered. You have depolarization, then repolarization, then hyperpolarization to bring us back to that resting state. And that is what you need to know when it comes to an action potential. So I hope you've liked this video, and if you have, then please do click on the like button and subscribe to my channel. If you haven't already done so, please do check out my revision platform, www.aiqchat.com.